In the previous video, we discussed finding the volume of a solid of revolution by the disk or washer method, which was based on the idea that when we partition a two-dimensional region using rectangles in the style of a Riemann sum, and then rotate that region, if the rectangles are perpendicular to the axis of rotation, that rotation forms each rectangle into a cylindrical disc, a flat cylinder that has a cross-section equal to the area of the circular surface and a thickness of the equal to the width of the rectangle. But what if those partitions, what if those rectangles were rotate about an axis to which they are parallel? In that case, we would not result in a disk, we would result in what is known as a cylindrical shell. For example, let's consider a region underneath a parabola, but only on the interval from 0 to the x-intercept. Now, any partition on this would result in a rectangle, such as this. If we were then to rotate this around the y-axis, note that the rectangle is vertically oriented, the same as the axis itself. They are parallel to each other. This rotation results in a cylindrical shell, which again, I am not a particularly good artist. A better visualization of this effect is in a video on the course homepage. But it ends up forming this cylindrical shell. Instead of a solid disc that is wide but flat, this is somewhat more like a washer where it has a cylindrical shape and then a portion removed from the middle of it. But in this case, it is not very, very flat. It's actually very tall. And the washer face is actually a very, very thin circle. So we essentially have a circle around the top of this with a bit of width to it equal to the width of the rectangle. And that circle is then got a projection in the vertical direction that causes this to become three-dimensional. The idea then is that each partition would create its own separate cylindrical shell in this manner. So our total volume would come from adding up the volume of all the cylindrical shells, much as the same way that in the disk and washer method, the volume of the three-dimensional object came from adding up the volumes of all of the cylindrical disks. So what we need to do here is find a way to describe the volume of a single cylindrical shell, and then in the same fashion as with the Riemann sum, expand that for every cylindrical shell that is created based on each separate partition of the two-dimensional region. And then through summation, and then through a limit, we can turn this into an integral. The trick here comes in taking a cylindrical shell and cutting it. We cut it in a direction perpendicular to the circular face of it. And then from there, we can unroll it. Once it is cut, we can unroll it and lay it flat. And when we do so, it becomes a rectangle. Technically speaking, it becomes a rectangular prism, a very, very flat rectangular prism. the thickness, the depth of this rectangular prism is based on how wide our partitions are. And we know that eventually those partitions will become smaller and smaller and smaller in width. But for now, we do have a thickness to this. We have a thickness on this dimension, and that thickness is the same thickness as the width of our partitions, which we call delta x. Now, technically speaking, the outer radius of the shell and the inner radius of the shell are actually slightly different. So with a slight bit of suspension of disbelief here, as these partitions get smaller and smaller and smaller, as the cylindrical shells get thinner and thinner and thinner, the difference between the outer radius and the inner radius, those two get closer and closer together until eventually the outer radius and the inner radius will essentially be the same thing. Meaning that when we unroll this, we don't have to consider the inner surface and the outer surface to have two different measurements. We can consider them to have the same measurement. And that measurement is equal to 2 pi r, the circumference of the circle. The third dimension then is, of course, the height of the cylinder, which is the easiest part. Thus, the volume of a single cylinder is going to be 2 pi r times h times delta x. Of course, the radius of the shell will be determined in part by which partition we are in. For example, if we are in a partition that is much closer to the axis of rotation, then we will end up with a cylindrical shell that has a much smaller radius. So our radius is going to be keyed into which partition we are currently in. Likewise, the height of the cylindrical shell is going to be tied into the height of the rectangle, the height of the function on that subinterval. So the volume of the ith shell is going to be based on a radius tied to the ith partition and a height tied to the ith partition. In that case, the approximate volume of the entire three-dimensional object then is going to be the summation from I equals 1 to I equals n of 2 pi times r sub I times h sub I times delta x, where r sub I is the radius of the disk, the radius of the shell, which, assuming we're rotating around the vertical axis, the radius should be equal to x sub I. And the height then would be equal to f of x sub I. Now, if we are rotating around a different vertical axis, then we would have to be much more careful about how we defined the radius. Very often, for that reason, the formula for this is given with the radius not as x sub I, but as a function of x. Because while it will be tied into the x value, it is the x value relative to the axis of rotation. For now, we will keep the axis of rotation on the vertical axis as we did with the disk and washer methods. What this results in then, when we put a limit in front of this, is it results in the volume being equal to the integral from a to b of 2 pi times x times f of x dx. This is the volume formula using cylindrical shells. Now, we're going to attempt to do this with the cylindrical shell method, but we're also going to work with a function that can be done with the method of the disk or washer method so that we can verify that the shell method is going to give us the correct results. So our example here is going to start by defining the region R as being the region bound by the graph of y is equal to negative x squared plus 4 and the x-axis on the interval from 0 to 2. And then we are going to revolve R about the y-axis. This is going to give us a region like we had at the beginning. Where we have the right side of a downward facing parabola our axis of rotation is the y-axis, so that our partitions are being done vertically, and thus rotation will result in cylindrical shells. The radius of the cylindrical shells will always be the x value of the right endpoint of the ith subinterval, and the height of the cylindrical shells will be the y value of the function at the right endpoint of the ith subinterval. So that if we want the volume of the three-dimensional figure, it will be the integral from 0 to 2 of 2 pi times x for the radius times negative x squared plus 4 for the height dx. This is a simple enough integral to evaluate. We can bring the 2 pi out in front. We can distribute the x into the negative x squared plus 4 to give us negative x cubed plus 4x. And this, being a polynomial integrand, is easily integrated. The antiderivative is negative x to the 4th over 4 plus 2x squared. And by the fundamental theorem, we will evaluate that at 2 and at 0 and subtract those. So we have negative 2 to the 4th over 4 plus 2 times 2 squared minus 2 pi times negative 0 to the 4th over 4 plus 2 times 0 squared. Where, fortunately, 0 to any power being 0 means that this entire second portion is going to evaluate to be 0. Which leaves us with just the first portion to evaluate. 2 to the 4th is 16, and 16 over 4 is 4. And then 2 squared is 4 times another 2 is 8. So we end up with 2 pi times 4, which is 8 pi. And that is the volume given by the cylindrical shell method. It would be a good idea then to verify this using a method that we are already familiar with. So we are now going to do another example of the same region rotated about the same axis, but this time we're going to do it with disks. The difference being that because we're going to be using disks, we're going to have to change how we set up our integral. So we have the same region R defined by this parabola. And we're still going to rotate about the vertical axis, but this time we're going to do this with the disk method. And in order to do that, that means we need our rectangles to be oriented perpendicular to the axis of rotation, so that upon rotation, this will form them into disks. Which means that we need this to be done with respect to y. And this is why we have the shell method as opposed to the disk method. We have them both because they give us an option. If we are rotating around a vertical axis, then to use the disk or washer method, which has a simpler integral formula, would require us to have to define everything in terms of y. We can leave it in terms of x, but that would require us to use the shell method, which has a slightly more complicated integral formula. Either way should produce the same result because they are producing the same object. So let's put that to the test. In order to put this in terms of y, we need to solve the parabolic equation for x in terms of y. So we have y minus 4 is equal to negative x squared, or negative y plus 4 is equal to x squared, and then a square root of both sides. Now, as we've seen before, this would result in a plus or minus in front of the square root. However, we can see that we are clearly dealing with only positive x values here, and that allows us to resolve the plus or minus by simply using the plus, because x is always positive. So by the disk method, our volume would be given by the integral from y equals 0 to y equals 4 of pi times r, which is negative y plus 4 under the square root, squared dy. We can, as usual, bring the pi out in front. The square actually cancels out the square root beautifully and leaves us with negative y plus 4. The antiderivative of which is negative y squared over 2 plus 4y, and that is evaluated at y equals 4 minus the evaluation at y equals 0. So we have negative 4 squared over 2 plus 4 times 4. And then it should be pretty clear to see here that if we substitute 0 for y, that's going to result in an evaluation of 0, and therefore cancel out the entire second portion of the fundamental theorem of calculus. So we're left with just the first portion. And negative 4 squared is negative 16 over 2 is negative 8. 4 times 4 is 16, and this gives us 8 pi. The same result that was produced by the shell method, but this time done with the disk method. This allows us to build faith in the shell method by showing that it is producing the correct answer, as verified by a method that we are already more familiar with and more comfortable with. It does also demonstrate that we have the option, that we can convert this to being in terms of y and thus use the disk method, or that we can leave it in terms of x and use the shell method.